Hello, good afternoon, everyone. It's my pleasure and privilege to introduce today's speaker to you all. And he's Dr. Manish Sinha. He had his bachelor's and master's in chemistry from Vinoba Bhave University in India, and his PhD in chemistry from Banara Hindu University in India. He's currently a postdoc in the Mechanical and Materials Engineering Department here in WPI. He was a postdoc fellow in chemistry department at University of the Free State in South Africa, and a researcher at CSIR National Metallurgical Laboratory in India. He was also so yeah, he's currently a postdoc here, and his projects are in the recovery of metal values from waste management and recovery of metal values from pickling solutions. So today he'll be giving us a seminar talk on hydrometallurgical recovery of metal values from secondary resources. And with that, I would welcome Manish. I'll just stop sharing. Share. Okay, before he starts, I would also add that Professor Powell mentioned that today's attendance would be a correct response to the poll that would be sent out. So it's encouraging everyone to please participate in the seminar. Thank you.
Thanks. Good afternoon, everyone, and thank you, Chinanya, for your kind introduction. And before starting my presentation, I would like to thank Professor Powell for considering me for this seminar. So topic of today's presentation is hydrometallurgical recovery of metal values from secondary sources. So my presentation will include a brief introduction to the secondary resources and hydrometallurgical process, followed by objective of my work and then results of discussion, in which I will discuss processing of two solid state and processing of two liquid waste, followed by conclusion and acknowledgement. So why processing of secondary resources is necessary? As we all know that metals are generally extracted from their minerals from primary resources. Those are minerals and ores of that particular metal. But due to continuous mining, because of the high demand of the metals, it has highly affected the grade of the primary resources. Just in case of, you can see in the table, yeah, the grade of copper mined in USA has decreased from 1.8% to 0.48%. It means the more mining has been undertaken to meet the demand of the copper metal, and means more mining means more waste generation and more power energy consumption. So what are the, and at the same time, it has not only degraded the grade of the primary resources, it has also partially degraded the primary source of some of the metal ions. So what are the possible alternatives to deal with such situation, to preserve the primary sources and to avoid the extra burden on the primary sources? Either we have to explore some new ore bodies and either use low grade ores. But the exploration of new ore body is very challenging task because of the dispersed nature of the minerals in the earth. And at the same time, using the low grade ores in the establishing facilities is very difficult because low grades ore need extra beneficiation states to enter the extraction stage. And at the same time, the stockpiles of these low grade ores are very limited. In that case, processing of secondary resources can offer a viable means to partially offset the need to mine and process virgin ores. So now the question arises, what are the possible secondary resources? We know that metallurgical and mining industries are associated with the large associated with large quantity of solid waste and liquid waste. The solid waste may be tailings, slag, flue dust, leach residue, while the liquid waste consists of pickling solution, electroplating effluents, bleach solution, and rinse wastewater. And in the last 30 years, we have seen a tremendous growth in the e-waste generation. E-waste are nothing but the end-of-life consumer product based electric and electronic products, which contain mobile, laptops, fluorescent lamp, etc. And as per one report, early 50 million ton of e-waste is generating worldwide, in which more than 60% is a metallic content. So all these metal sources are not only high rich in metal concentration, but contain metal ion concentration more than their primary sources. So if they can treat it properly, they can not only serve as a source for metal ions, they will also mitigate the pollution problem that occur due to the improper handling of these wastes. So the metal recovery process generally include three processes: pyrometallurgy, hydrometallurgy, and electrometallurgy. Solid waste generally go for the many physical separation, physical beneficiation process before entering to the main extraction process. And sometimes the combination of all three processes are used for the recovery of metal ion from these waste. And all these processes have their own advantages and disadvantages. And based on the ease of operation, low cost involvement, and high purity and flexibility with the synthesis of the products make the hydrometallurgical process is the best process for the recovery of metal ion from secondary sources. So hydrometallurgical process consists of numerous unit operations such as leaching, which is nothing but dissolution of the solid waste in the acid solution, and followed by the separation of the metal ion from leach nickel by solvent extraction, and then stripping for the to get the pure metal ion solution, and then precipitation and electrowinning to get the metal ion in pure form. So each stage is depends upon many parameters, like leaching depend upon the mineralogy of the ore, and at the same time type of acid, temperature, agitation speed, etc. While solvent extraction depend upon the nature of the aqueous phase, nature of the extractant, and many other temperature, etc. So based on this, so in coming slide, I will discuss about the recovery of metal ion from two solid waste, that is samarium cobalt magnet scrap and neodymium iron boron magnet, and two liquid waste, which is spent iron pickle liquor and spent brass pickle liquor. So first of all, I will discuss about the recovery of metal ion from samarium cobalt magnet scrap. So samarium cobalt magnets are generally used in high military applications like precision guide missile because of this higher magnetic strength and its ability to stand at high temperature. And during the formation of samarium cobalt magnets, 50 to 30% of the raw material is wasted as scrap. And to the best of my knowledge, it is the only secondary resource of samarium cobalt magnet. So whatever samarium is produced worldwide is brought into the formation of samarium cobalt magnet. So following approach I have followed for the recovery of samarium and cobalt from magnets. First I have crushed and sieved the samarium cobalt magnet, then followed by demagnetization, leaching in acid to dissolve the samarium and cobalt contained in solution, followed by acid recovery, and then separation of samarium cobalt by solvent extraction, and then synthesis of value-added product of samarium and cobalt. So this samarium cobalt magnet was collected from Defense Metallurgical Laboratory of India. So as you can see that it was crushed and sealed, you can see that it's highly magnetic in nature. The XRD analysis suggests that it's samarium SmCO5, all the phases The only one phase is present in the samarium cobalt magnet, which is SmCO5. The chemical analysis suggests that high concentration of samarium cobalt present in this magnet with some minor impurities of iron. So some preliminary experiment was carried out with this magnetic powder, and because of the high magnetic power, it tends to bind with the magnet and thus reducing the leaching efficiency of samarium cobalt in the solution. So further experiment was carried out with the roasted samarium cobalt magnet. So roasting temperature was determined by TGA analysis, and it was observed that at 850 degrees Celsius, samarium cobalt magnets completely oxidize into mixed samarium cobalt oxide. So XRD also confirmed the presence of mixed samarium oxide and cobalt oxide phase. So this roasted magnetic powder is further used for the leaching of samarium and cobalt. So in order to determine the suitable excipient for the leaching of leaching of samarium and cobalt from the roasted magnetic powder, various mineral acid was used to determine which one is more efficient to leach the samarium and cobalt from the roasted magnetic powder at 95 degrees Celsius using the pulse density of 100 GPL and keeping the constant concentration of acid 4 molar. So you can see that in the figure, the nitric acid is highly selective for samarium, while cobalt recovery is very less in nitric acid solution. While in case of sulfuric acid, the samarium recovery decreases with increase in the time, while cobalt recovery is also less. The decrease in samarium may be due to the precipitation of samarium sulfate in the solution because of common effect of the sulfate ion. So finally, some experiment was conducted in hydrochloric acid, and it was observed that hydrochloric is able to simultaneously leach out both samarium and cobalt from the roasted magnetic powder. So further experiment was carried out with the hydrochloric acid. So first of all, effect of hydrochloric acid was studied at 95 degrees Celsius using the pulse density of 100 GPL, and the hydrochloric acid was varied from 1 molar to 4 molar, and as can be seen, the recovery of both samarium and cobalt increased with increase in the hydrochloric acid concentration, and in 120 minutes, in 2 hours, almost 100% of samarium leached out in the solution, while cobalt leached out in 3 hours in the hydrochloric acid solution. So further experiment was carried out only using 4 molar of hydrochloric acid. So effect of temperature was also conducted using the 4 molar hydrochloric acid, keeping the constant pulse density of 100 GPL, and the temperature was varied between 65 to 95 degrees Celsius. And I think this is as expected. Both the dissolution and recovery of samarium and cobalt increase the temperature, because with increase in temperature, diffusion of hydrochloric acid increases. So that's why the recovery is also increased. So it can be seen that 95 degrees Celsius is more optimum for the leaching of samarium and cobalt using the hydrochloric acid solution. The optimum condition was found that 4 molar HCl, 95 degrees Celsius, 100 GPL per density, and 500 RPM agitation speed, and 180 minutes. So in 180 minutes, all the samarium and cobalt leached out from the roasted magnetic powder into the solution. The effect of agitation speed was also studied, and it was observed that the agitation speed doesn't affect the leaching of the samarium and cobalt. So using the data obtained at different temperature, the leaching kinetics of samarium and cobalt was also determined. So for any solid liquid system, the leaching kinetics determined by shrinking pore model. This says that the leaching is occur by the diffusion of reactant into the solid surface, either by through the solid film layer, or either by the reacted solid product layer, or direct by chemical reaction. So data was fitted to the both models, chemical control model and diffusion control model, but it was observed that chemical control model fit good to the data obtained at different temperature. You can see that from the high correlation coefficient value, which suggests that the leaching process is controlled by chemical reaction on the solid surface. The activation energy was also determined for the samarium and cobalt leaching, and you can see that the high leach activation energy also confirms that the leaching process is chemically controlled, because the activation energy for chemical control model is more than 40 kilojoule activation energy. For the diffusion control, the activation energy is below 20 kilojoule. So in order to confirm that the leaching is follow the chemical reaction, so we have I have also analyzed the leach residue obtained at different time. So you can see that with increase in time, the particle size is also getting decreased. So with the action of acid, all the you can see the particle size is corroded from all sides and ultimately decrease into a rather more smaller size, and with increase in time, everything is dissolved in the acid solution. The chemical analysis also suggests that the simultaneous dissolution of samarium and cobalt in the lead solution, and in 120 minutes, all the samarium dissolved in the hydrochloric acid, while cobalt remain as residue, which further on leached out in 180 minutes, leaving no residue in the system. So after leaching this, why is coming this?
Deadline. Oh, that somebody annotated it, when they logged it, somebody annotated by mistake.
So after leaching samarium and cobalt from the roasted magnetic powder, the samarium and cobalt was separated. So by solvent extraction, before separation of the samarium and cobalt, the HCl was recovered from the solution by vacuum distillation process at 70 degrees Celsius. And the crystallized residue obtained after the supersaturated solution of the leach liquor, it was dissolved in water, and then finally solvent extracted with the help of Sinus 572. Sinus 572 is the mixture of phosphonic and phosphonic acid, and it is a mild extractant. So effect of pH was also studied for the extraction of samarium and cobalt, and you can see from the figure, samarium selectively extracted into the Sinus 572 extracted at pH 2, while leaving copper behind in the refrigerant, while leaving cobalt in the refrigerant. So cobalt extraction was observed only with the high concentration of Sinus 572, and as can be seen, more than at pH 5, almost all cobalt extracted into the organic phase. So from the loaded organic phase, samarium and cobalt both were selectively stripped with 1 molar HCl solution to get the purified solution of both samarium and cobalt. And this purified solution was further used for the synthesis of samarium oxide and cobalt oxide via oxalate precipitation method. So XRD confirmed the formation of samarium oxalate decahydrate and cobalt oxalate dihydrate, which was roasted in 800 degrees Celsius and 400 degrees Celsius respectively. The roasting temperature was determined by PGBK analysis, which further gives us pure samarium oxide and cobalt oxide. This for as synthesized samarium oxide and cobalt oxide was characterized by XRD, same in chemical analysis. So XRD confirmed the phases of samarium oxide and cobalt, pure phases of samarium oxide and cobalt oxide. While SEM says that the samarium oxide generally agglomerated kind of particle with some globular particle and some plate kind particle of 2 to 5 micron size, while cobalt oxide is mainly prismatic particle of 2 micron size, and some globular shape particle is also there, but with of 0.5 to 1 micron size. So highlight of this work is that samarium cobalt can be used for the recovery of samarium and for the recovery of samarium and cobalt. And HCl is the efficient leaching agent for the recovery of samarium and cobalt. And Sinus 572 can be used for the separation of samarium and cobalt. And from the purified solution, it is possible to synthesize high pure samarium oxide and cobalt oxide from it. So samarium cobalt can act as a potential second reducent for samarium and cobalt. So the next solid waste is neodymium iron boron permanent magnet. And because of the high magnetic strength, the magnetic strength of neodymium magnet, then commonly used unequal ferrite magnet, even a tiny size of this magnet can be very effective. And because of this property, it is used in various applications from hard disk drive, washing machine, electrical bike, electric vehicle, and now it is in wind turbine generator. And you can see that lot how much amount is used for the used in the wind turbine generator, like more than 250 kgs to 650 kgs of neodymium iron boron magnet is used in the wind turbine. So these waste magnets generated after their end of life can act as a possible secondary source for neodymium and other rare earth metal from the neodymium permanent magnets. So there are various process has been proposed and used for the recovery of neodymium and rare earths from the neodymium iron boron magnet. So general pyrometallurgical and each process has their own limitations. You can see that in general pyrometallurgical process where rare earth oxide is first the rare earth is converted into the oxide and iron is melted into the iron metal. But the separation of this one is very difficult and sometimes it need high purity of input and it need high temperature. The recovery is sometimes very low because it's highly dependent upon the temperature. And another process is hydrogen deprecipitation method where the magnet is demagnetized in presence of hydrogen gas and then followed by the sintering of neodymium rare earth hydride to the magnet again. So this also is not suitable for the mixed express as the magnet which are oxidized. And it also need to remove the coating layer from the neodymium iron boron magnet before the processing. And another process is chemical vapor transport. And because of the chlorine gas is highly corrosive and difficulty of rare earth chloride from the alkaline solution, alkaline chloride is very difficult. And at the same time, it needs high temperature. Another method is electrolysis using molten salt electrolysis, where the cell design is very critical and the behavior of molten salt is also very critical because it can react with the refractory of the cell and the gas involved at the anode, which is basically fluorides, are very difficult to handle. So it needs extra care. And at the same time, molten salt electrolysis extraction is also very difficult to handle because of the high temperature. And there is one another process which is to selectively dissolve the neodymium into the magnesium and then use the vacuum distillation process. And I think Professor Powell Research Group is working on this field. So this is also a promising area. But in this study, we have used hydrometallurgical process for the recovery of rare from the neodymium magnets. So the conventional hydrometallurgical method is to use the demagnetized neodymium iron boron magnets and then leach out in acid solution to leach out simultaneously both iron and rare earth, followed by oxidation of iron and then precipitation of iron and the iron hydroxide to get the iron ring solution. But the problem with this precipitation method, precipitation stage is that during the precipitation of iron hydroxide, more than 30% to 40% is rare earth end up in the hydroxide of the iron. So we have proposed here a oxidation roasting to convert the iron into the hematite phase and neodymium other rare earth into the oxide phase, followed by a selective leaching of the rare earth and then to get the rare earth rich solution and iron oxide in the residue. So the waste magnet we have collected from the Reason Power Tech Private Limited, which is India's third largest wind energy company. And XRD initial characterization was carried out with XRD and SCM. XRD confirmed the presence of ND2 F14G phases in the magnet. And chemical analysis it can be seen that it shows that high concentration of rare earth present in the neodymium iron boron magnets. So before going for the oxidative roasting, the first neodymium magnet is demagnetized above the Curie temperature, followed by the crushing and grinding. And the oxidation roasting temperature was determined by TZI analysis, as can be seen that 850 degrees Celsius is enough to convert all the metallic content into the oxide phase. The XRD of the oxide phase of the oxidized material suggests that the conversion of all the rare earth and iron into the oxides. So the major phases is neodymium oxide and hematite only. So this roasted magnetic powder is used for the leaching process. And you can see that potential pH diagram. So it is evident that it is possible to leach out neodymium selectively from the roasted magnetic powder and leaving behind iron oxide in the residue. So first, few preliminary experiment was carried out from the roasted magnetic powder obtained at different roasting temperature. And as can be seen, the recovery of rare earth is almost same, but the recovery of iron is decreased with increase in the temperature of increase in roasting temperature. This suggests that at lower temperatures only partial oxidation of hematite iron is occurred, while at the higher temperature almost all iron is converted into iron oxide, which is very stable and not dissolved in acidic phase. So in order to determine the suitable leaching agent, first preliminary experiment was carried out using different kind of mineral acid, H2SO4, nitric acid, and hydrochloric acid. And as can be seen, H2SO4 is not very much effective for the recovery of rare earth, while nitric acid is effective, but the recovery is very less in comparison to the hydrochloric acid. So organic acid were also tried for the leaching experiment, and it was only 20 to 30% recovery was observed for the rare earth. So for the further experiment, hydrochloric acid was used as a potential leachant for the recovery of rare earth from roasted magnetic powder. So first of all, effect of acid concentration was studied using the 100 GPa per density at 95 degrees Celsius. So as can be seen, with increase in the hydrochloric acid concentration, the recovery of rare earth increased. At the same time, the recovery of iron is also high iron observed at the high acidic concentration. But in the lower acidic concentration, you can see that the iron recovery increase and then decrease. This may be due to the because at lower concentration of HCl, all the hydrochloric acid involved in the leaching of rare earth, and because of the all acid is involved in the leaching of rare earth, the pH of the system increased, and due to increase in the pH, whatever iron is leached out in the solution is precipitated as the iron hydroxide. So use of low acid is very effective here for the recovery of selective recovery of rare earth from the roasted magnetic powder. So further experiment was carried out using using 0.5 molar HCl. The effect of temperature was also studied. The temperature was varied from 75 degrees Celsius to 95 degrees Celsius. And as can be seen, with increase in temperature, rare earth recovery is also increased, and iron recovery decreased with increase in temperature because of the early hydrolysis of the iron, whatever iron is left in the solution. And from the leach Nikel analysis suggests the presence of only rare earth and very minor concentration of iron in the solution. So it's highly pure rare earth leach solution is obtained after the leaching. So leaching kinetics was also determined for the recovery of rare earth and from the roasted neodymium magnet powder, and both chemical control model and diffusion control model was used. So as can be seen, that both model is having correctly fit to the all the data fit to the both the models, as can be seen from the correlation coefficient values. So it suggests that the leaching kinetics follow the mixed control process, and the data also fitted to the mixed control model, as can be seen. The high negation coefficient suggests that the leaching kinetics follow the mixed control reaction. The activation energy was also determined using the slope of the mixed control model. So the intermediate activation energy of 30 kilojoule suggests that the leaching kinetic control by both diffusion and chemical control reaction. So further, in order to confirm that the reaction is followed by mixed control model, the leach residues was also characterized, obtained at different time. So you can see that with increase in the time, the particle is much corroded than the initial reaction, and the analysis of the particle size also suggests that there is a very minimal decrease in the size of the particle. This suggests that the rare earth is first extracted by the chemical reaction on the surface, and then iron oxide is acting as the inner product layer, which provide the resistance against the diffusion of the HCl into the core material of this roasted magnetic powder. So that thus is confirmed that the leaching kinetics follow the both chemical reaction and diffusion control process. So from after the leaching, from the leach liquor, rare earth mixed rare earth oxide was produced by a oxalate precipitation, and the leach residue contain only iron oxide, as it is evident from the XRD and chemical analysis, which says that the leach residue contain hematite of purity 93%, while the rare earth mixed rare earth oxide prepared is purity of 98%, is having the purity of 98%. So highlight of this study is that neodymium iron boron magnet can act as a potential secondary sources for the recovery of rare earth metals. The next secondary resource is the liquid waste generated in the steel industry, which is spent iron pickle nickel. In order to improve the corrosion property, steel surfaces are generally galvanized in molten zinc bar. So before going for the galvanization, steel surfaces are generally cleaned by dipping into an acid solution. This cleaning process is known as the pickling process. And due to repeatedly use the same bar for the cleaning purpose, impurities build up into the solution. And you can see that the high concentration of zinc and iron can build up in the leads in the pickling solution, and after some time it became ineffective for the further pickling process, so it rejected. And because of the high acid and metal content, it cannot be disposed of before any pre-treatment. And every year 2 billion liters of steel pickle generated is generated worldwide, from which a high amount of iron oxide production is possible from this solution. The conventional processing of spent iron pickle liquor includes neutralization with lime, and the sludge generated is either dumped as a landfill or stored for the further processing. While in another process, first the HCl is recovered by evaporation, and the iron oxide is crystallized at a high temperature. But both these processes have their own drawbacks, because during the neutralization with lime and sludge formation, it creates the environmental pollution. At the same time, large amount of acid and metal values are also lost in the sludge. And in second process, the high concentration of zinc in the solution creates problem in the purity of the iron oxide synthesis. So we have used a solvent extraction method to separate the iron and zinc from spent iron pickle liquor. So spent iron pickle liquor we have used for this study is containing high concentration of HCl 73 GPL, while iron 2 is 20 GPL and zinc is 50 GPL. And we have used Sinex 923 extractant for the separation of iron and zinc. So the selection of extractant is highly dependent upon the nature of the aqueous phase and the nature of the metal ion in the aqueous phase, as can be seen from the specification diagram. At higher acidity, iron and zinc both present as a higher fluorocomplex, and this fluorocomplex can be extracted by iron pair formation or by outer assembly formation. And Sinex 923 is the best extractant for this mechanism. So first of all, effect of extractant concentration was also studied. The Chinese 923 was varied from 0.25 molar to 1.7 molar acidity concentration, and the extraction time was maintained to 30 minutes, and the phase ratio was maintained 1:1, 1:1. So as can be seen, with increase in the extractant concentration, the extraction of iron and zinc and HCl is also increased. But ferrous ion remains stable in the solution, it doesn't extracted into the organic phase. The log plot of the says that for 1 mole of zinc extraction, they give a slope of 2, which suggests that for 1 mole of zinc extraction, 2 mole of extractant is involved, and the reaction can be expressed by the following equation, which suggests that the solution mechanism is involved for the extraction of iron and zinc. Further, for the complete extraction of iron and zinc, loading capacity was also studied by contacting the same organic phase with the fresh aqueous solution, and as can be seen in 2 stages, almost in 3 stages, almost complete zinc extraction is observed, and in with each stage, iron is also built up in the organic phase. So using this data, the Mercalli diagram was also plotted to determine the theoretical number of stages required for the complete extraction of zinc and iron from the spent pickle liquor. And you can see that at 3 stages is enough for the complete extraction of iron and zinc from spent iron pickle liquor. The simulation of in order to prove this, the simulation of counter current was also studied, and it says that at the end of 3 stages, almost 50 GPL, almost complete iron zinc is loaded into the organic phase with 9 GPL of iron. So finally, from the loaded organic, zinc and iron was separated by the stripping process. So instead of using the general stripping process, which include reaction with mineral acid, we have used precipitation method because we know that iron is forming very high soluble oxalate complex in the oxalic acid solution, while zinc form very insoluble oxalate complex. So it is possible to separate both at the same time. So if you treat the organic phase with the oxalic acid solution, iron will remain in the solution while zinc will precipitate as a zinc oxalate. So you can see from the figure, with increase in the oxalic acid concentration, almost all iron is stripped in the solution, while on 50% of zinc is precipitated as a zinc oxalate. Further optimization says that at the phase ratio of 3:1, it is possible to precipitate out all the iron and zinc from the loaded organic phase. So the zinc separated as a zinc oxalate was characterized by XRD, and which suggests that the formation of rather pure zinc oxalate dihydrate, and from this obtained zinc oxalate, zinc oxide was synthesized by roasting it in the air. The roasting temperature was determined by TGI analysis. It says that at 450 degrees Celsius, heating the conversion of zinc oxide to zinc oxide is very possible. And XRD also suggests the formation of pure zinc oxide phase. And the ACM of the synthesized zinc oxide says that zinc oxide is mainly composed of needle shaped particle and some globular shaped particle. Now the ferric oxalate solution that obtained after the stripping was also utilized for the synthesis of iron oxalate and followed by iron oxide. So ferric oxalate is highly stable in aqueous phase, while ferrous oxalate can be precipitated from the solution by reducing it with the iron powder. So ferric oxalate solution was reduced by iron powder at 50 degrees Celsius in 1 hour using the stoichiometric amount of iron scrap, and the XRD confirms the synthesis of iron oxalate dihydrate. And the TZ analysis says that the iron oxide dihydrate can be converted into the iron oxide by heating it to above 300 degrees Celsius. The XRD analysis suggests the formation of hematite by decomposition of iron oxalate, while ACM analysis said that hematite particle is mainly composed of covalent ball-shaped particle and cube-shaped particle, and the purity of as obtained iron oxide is more than 99.9%. So highlight of this study is Sinus 923 can be used for the simultaneous extraction of zinc and iron from the spent iron pickle liquor, and by using the precipitation stripping method, it is possible to separate both iron and zinc in the same stage, and from the purified solution, it is possible to synthesize the iron oxide and zinc oxide particle. So the last waste I have used is the spent brass pickle liquor, same as iron pickle liquor. It is generated in brass industry and copper alloy industry. So to remove the oxidized layer from the copper and brass surface, it is generally cleaned in the sulfuric acid bath, and due to repetitive pickling in the same bath, metallic impurities like copper and zinc build up in the bath, and it is no more effective for the further pickling process. As can be seen that brass pickle liquor may contain high concentration of sulfuric acid and high concentration of copper and zinc. So because of high concentration of copper and zinc, it can serve as a possible secondary source for the recovery of copper and zinc. And for per ton of copper and copper alloys, 90 liters of spent brass pickle liquor is generated. And because of its hazardous nature of the due to chromium content and because of the acidic content, it cannot be disposed of before any further pre-treatment. So we have used solvent extraction method to separate the copper and zinc. So before separation of copper and zinc, H2SO4 was also separated using solvent extraction by using amine-based extractant, while copper and zinc was extracted using oxime-based extractant, which is mix 984N, which is the combination of aldoxime and ketoxime-based extractant. Because this extractant can form very stable complex with both copper and zinc. So before going for the copper and zinc separation, first of all, the sulfuric acid was also extracted by solvent extraction using amine-based extraction, which is trihydroxide amine. And at the phase ratio of 2:1, all the acid is loaded into the organic phase, which is further stripped with water, distilled water at 50 degrees Celsius to regenerate the organic acid, and the dilute acid can be used for the further pickling process. From the acid-free solution, the iron was removed because it can be extracted during the extraction of copper and zinc. So first to minimize the effect of iron, first it was precipitated in the form of iron hydroxide by adding a dilute sodium hydroxide solution, and from the iron-free solution, copper and zinc was separated by solvent extraction using mix 984N extraction. So first of all, effect of pH was studied, and you can see that copper is selectively extracted at pH 3 around pH 4, while zinc extraction is started above pH 4 and completely extracted at pH 6.4. So log V versus equilibrium pH plot suggests that for 1 mole of zinc and copper extraction, 2 moles of pH is released into the solution. Thus confirm this mechanism. So further experiment was carried out at different phase ratio to determine the theoretical number of countercurrent stages for the complete extraction of copper and zinc. So for copper extraction, pH half was used 2.5, while the zinc extraction pH 5.5 was used. And as can be seen from the phase ratio variation, it is possible to completely extract the copper from the iron-free pickle solution in 2 stages using the phase ratio of 2:1, while zinc extraction is possible in 3 countercurrent stages at the same phase ratio using 1 molar leaks 984 N. So in order to establish this metal theory plot, the countercurrent studies were also carried out in a mixer settler unit, and the results are like this. In the 2 stages, almost complete copper is extracted into the organic phase, and from the copper-free solution, before going for the zinc extraction, chromium is precipitated. Because chromium start to precipitate above pH 5.5, so it is necessary to remove it from the system to get the pure zinc solution. So the countercurrent study says that in 3 countercurrent stages, almost complete zinc is extracted in the organic phase. This loaded organic further is treated with 1.5 molar H2SO4 to get the pure solution of copper and zinc. Now this pure solution of copper and zinc is used for the synthesis of copper metal and zinc oxide by hydrothermal process. So as can be seen from the potential pH diagram, the reduction of copper is possible at any pH, even at the using the 1 atmosphere hydrogen gas. But in this process, in this experiment, we have used high temperature and pressure to enhance the kinetics, to enhance the precipitation of in less time period, precipitation of copper metal in less time period. And while from the zinc purified pure zinc solution, zinc oxide was synthesized under hydrothermal condition of high pH, and the temperature was used the same 150 degrees Celsius. The highly basic solution was chosen to ensure the purity and fast growth rate of zinc oxide. So after the hydrothermal reduction, the synthesized copper metal powder was characterized by XRD, and you can see that XRD confirmed the presence of pure copper phase, while ACM of this synthesized copper powder says that copper metal powder is generally composed of globular shaped particle with 50 to 100 micron size. While the zinc oxide was also characterized with XRD, XRD confirmed the presence of pure zinc oxide phase, while ACM study says that the zinc oxide particles are mainly composed of rice grain shape of particles with 0.5 to 1 micron size. So highlight of this study is that VIX 984 and can be used for the recovery of copper and zinc. Copper can be selectively extracted at lower pH, while zinc can be extracted at the higher pH. And from their respective purified solution, zinc oxide and copper metal powder can be prepared by hydrogen reduction and hydrothermal process. So conclusion of this presentation is that all these studied secondary resources can act as a source for the metal extraction and metal production. Thank you. And I would like to thank my supervisor in PHU and my supervisor at CSI National Metallurgical Laboratory and my lab mate and all other technical staff that those who helped me during this study. Thank you. Thank you very much.
Okay, so take any questions you want to.
Yeah, sure.
A lot of people are not going to get full credit, it seems. Great. One question. In Sumerian cobalt, you mentioned that shrinking core model, and so that diffusion kinetics. I would expect something like that for neodymium leaching from a magnet where you have to diffuse the neodymium out. But in the case of Sumerian cobalt, if both of them are dissolving, then I'm curious, why do you get this kind of
For the samarium cobalt magnet, the leaching, uh, leaching model, it follows the chemical control model. So because there is no product layer formation in the samarium cobalt magnet, because both the metals ion are simultaneously get leaches out from the roasted magnetic powder. So there is no diffusion in the diffusion of HCl. So whatever reaction is occur on the surface of this system. Yeah.
It's the-
Sinking core model, yeah, sinking particle, sinking core model, yes.
Well, it's just after, 12:50, so, and I'm seeing those other things, but Jake has an announcement for,
Yeah, which, I don't know, if I can pop it up or not, but just one second. This one's. Yeah, so